thank you very much to the organizers for giving me the opportunity of giving these lectures. I welcome questions. That's the main issue. So you can raise your hand. I mean, I'm not going to ask for questions because then I forget, because I get too much into what I'm saying and I forget. But if you raise your hands, I do look at you. And so if you raise your hand, please, you can ask during the lectures or actually write down if you want, and then we will have long sessions of questions and answers. And you know, each group, each large group gets its own dynamics. So if there are a few people who ask questions, it's like melting the ice, and then people start asking questions, actually. So this is the most rewarding part for a lecture, is that actually there are questions, because of course you don't say everything, you don't explain everything. And as he said, there are no silly questions. Maybe there are silly answers, but not silly questions. Okay, so let us start. So I decided to separate my lectures into two parts, because I don't know exactly how long it will be. So the first, how long it will take me to go to the first part and then through the second. So this first part will lead us for sure through the first and second lecture. And then at the third, I don't know if at the beginning or in the middle, we are going to change to the second part. So the first part will have a brief introduction to the observational evidence for dark matter. Then we will say actually what we know about the dark matter. What we know about the dark matter defines what the problem is. And this has implications for the dark matter candidates that we will talk. Well, I don't know if any of you know all these acronyms. There are plenty of different acronyms in this field, in all fields, but in particular in this one. And I hope that you are going to be acquainted with most of them after my lectures. At least you're going to have seen them and maybe laugh at them. And then I'm going to cover some of the dark matter production mechanisms. And then later on, in the second part, we are going to talk about laboratory searches and indirect searches, and maybe some hints and where we are with hints on dark matter, etc. Okay, so first of all, let us see our local universe. So the building blocks of the universe are galaxies. Galaxies, this is our galaxy, of course, an artist's rendition of our galaxy. We live in a bar galaxy, disk bar galaxy. The sun is at about 2/3 of the radius of the disk out. And this is the nearest dwarf galaxy. Our galaxy, all galaxies have many satellites. And this is the nearest, the Sagittarius dwarf galaxy, which would appear very visible in the night sky if it were not, because it is from our location behind the center of the galaxy where there is a lot of dust, and so we cannot see in the visible, the center of the galaxy or anything that is behind. Our galaxy has many satellites, all galaxies do, and these are some of the very well-known older ones, like the large and the small Magellanic Clouds, etc. But now we know already more than 60, many of them found in the last 20 years in different searches. Some of the last one by this collaboration, the DES. And they are mounting. They are smaller and more dark matter dominated. We live, all galaxies are organized in groups. We live in a local group in which there are 3 major galaxies, ours, Andromeda and Triangular Galaxy, and many, many dwarf galaxies that are bound either to one of them or to the local group. So our local group is like a small town in the periphery of a very big city. The very big city is the Virgo cluster. Always in these plots, our galaxy is in the middle. This is the Virgo cluster. And there are many other clusters. At the level of superclusters, so clusters form superclusters, the organization is better described in terms of filaments, walls, and voids. You can see several voids here labeled in red, and so on. So what all these structures have in common is that they are all dominated by dark matter. They are essentially structures in dark matter with a little bit of visible matter that allows us to trace what is going on. And of course, not only galaxies and galaxy clusters, but also there are indications of dark matter in the early universe that I will mention in a moment. So the dark matter problem has been with us since the 1930s, so for about 90 years. Maybe Fritz Zwicky was not the first. I'm not sure of the history, but one of the first. And here you see in a paper in 1933 in German. German was the language of science before the Second World War. And you can see here dark, cold matter. Of course, dark matter, dark, is a misnomer, is a wrong name, because this is dark, and very dark. This is dark because it absorbs light. But in reality, it should be invisible matter. In any case, we have lost our right to rename this. The name is stuck. And so we are stuck with the wrong name. In the 1930s, what Fritz Zwicky saw is that the galaxies bound to the Coma cluster, a nearby cluster, moved too fast to be gravitationally bound to the cluster just by the visible matter. He used the virial theorem that you may have seen. This is a very simple example of the virial theorem. Consider just the motion of one planet around the sun. So here you have on this side, this is the force equal mass times acceleration. Force is the g, the mass of the sun, the mass of the planet over r squared, equal to m mass times acceleration. The acceleration is a centripetal acceleration, v squared over r. Here I took r squared and r, one of the r downstairs goes away. And here you have that the potential energy is equal to twice the kinetic energy. So this is what happens in all virialized systems, namely systems that reach equilibrium. And so you can, by measuring the kinetic energy, then you can see how much mass in total there is. And there was not enough mass to account for these galaxies to remain bound and not escape from the cluster. The same argument was applied after to gas. Gas moves too fast, namely it's too hot. Hot gas is ionized and emits X-rays. And so by measuring the amount of X-rays, you know how hot is the gas, and the gas in the cluster wouldn't have been bound, but just the matter that you can see alone. Another way of measuring the whole matter in a cluster is through gravitational lensing. So light is deflected by gravitational attraction, and the lensing effect depends on the whole mass. And so putting together all these elements, this different type of data, one can see that in clusters there is 6 times more mass than you could assign to all the luminous objects. Namely, you can count the mass in stars, the mass in dust, the mass in gas, and you are missing a very large amount, actually, 6 times more. But in the 1930s, this was a problem, but people didn't realize that there was a fundamental problem. This fundamental problem became very clear in the 1970s. So the 1970s was a moment in which the two standard models, one in cosmology and the other in particle physics, became established. So in the late 1960s is when the cosmic macro radiation was detected. And that proved the Big Bang as the model of cosmology. And in 1974, the charm quark was discovered that completed the second generation. And before the second generation of quarks was completed, the standard model of elementary particles could not be applied also to quarks. And so nobody believed it, actually. So only after 1974 it was established. And this is the moment, 1970s, in which people realize, hey, there is dark matter, and it cannot be accounted by particles in the standard model. Now, what happened in the 1970s? Vera Rubin, here you can see her, and others, actually, found that the rotational curves of galaxies are flat. What are rotational curves? You get the average velocity of things, luminous objects that are orbiting the galaxy, even luminous objects outside the disk. Actually, the disk of this galaxy finishes about here. And these luminous objects trace, of course, the amount of matter that is within the orbit. So applying the same thing, force equal mass times acceleration, you can see that the orbital speed, so the orbital speed as function of the distance of the radius of the orbit, in order for the velocity to be constant, the mass has to increase with the radius, even where you have no light. So the mass within an orbit increases linearly with the radius. So there is more mass than you can assign to luminous objects. And so galaxies like ours have a very extended dark halo, which contains about 85% of the total mass of the structure. So the little spiral that I show you at the beginning in this artist rendition is only 15% of the mass of the whole structure. In general, in galaxies, there is 4 times as much matter as the one that we can see, assigned to things that you can see. So you can see actually that there is also dark matter that is bound to clusters and not bound to every single galaxy within a cluster. At the largest scales, we have to use general relativity, or if there are other preferred covariant theories that replace or change general relativity, whatever is your preferred one. But you have to use general relativity in order to analyze different type of data. Here there are supernova type 1a, which are the standard candles, the brightest standard candles that we can use. The farther out, they go farther out. This is the largest scale structure of the universe, this cosmic macro background radiation, and the Baryon acoustic oscillations that I will explain briefly in a moment, a little bit better what they are. So all of this leads us to the conclusion of this double dark model, in which 95% of the content of the universe is in dark energy and dark matter. Dark energy has repulsive gravitational interactions, so not to be confused with dark matter. And so this accounts for 69%. The other 31% is in matter, and dark matter has gravitational interactions like the matter we know, like planets and stars and so on, but we cannot see it. And it accounts for about 26% of the content of the universe. Now, see, all this data confirm this Big Bang model of a hot early universe expanding adiabatically, and that means that the temperature decreases inversely to the size of the universe. So as the universe expands, the temperature decreases, and the expansion of the universe is quantified by this. It's called a scale factor that multiplies all the linear scales in the universe. Usually the scale factor is taken to be 1 at present, and so in the past it was always smaller than 1. And the temperature is inversely proportional to this factor, the scale factor. So this is sort of, this you have seen, I guess, this plot. It has a lot of different type of information here. But so the scale factor, the fact that the universe is sort of expanding, is indicated here with this type of funnel type of thing. So here on the right, we have the present time. You see us like the thinker of Rodin there. Not all of us think, but in any case, there we are here. And then also photons and neutrinos and black holes and so on. Then moving back in time, you have the formation of a structure. So if you run the picture, yes?
Yeah, so since the questions, we are recording all this talk, so that you will be available, you can look at them afterwards. So I'll ask all the questions to be asked in the microphone.
I can repeat if you want.
How do we get this proportion between the dark energy and dark matter?
This is local conservation of entropy. Mm-hmm. The entropy is conserved. The entropy goes as T cubed. The entropy is dominated by radiation. The entropy in radiation goes as T cubed. And therefore, in a comoving volume, the comoving volume is one that only changes because of the expansion of the universe. So if I have 1 cubic meter now, and then I multiply this cubic meter by A cube, right? Mm-hmm. A is the scale factor, mm-hmm. Then I will have the same, smaller and smaller and smaller, but changes only because of the expansion of the universe. Mm-hmm. And so S times the volume is conserved. Mm-hmm. And therefore, T cube, A cube is constant. Mm-hmm. And so you have conservation of entropy, mm-hmm. tells you that actually there is, then T goes as 1 over A. Mm-hmm. Mm-hmm. Yeah, there is a degrees of freedom. When the entropy is the degrees of freedom of entropy multiplied by T cube, mm-hmm. right? So when there's a change of degrees of freedom, namely how many particles and type of particles you have in the radiation, and it changes between a few now to, if you consider all the particles in the standard model, it becomes 100 mm-hmm. at temperatures that are above 200 GeVs. Mm-hmm. And so, but since this comes with a square root, a cubic root of the, then it doesn't change that much. Cubic root of 100 is, less than 10. Mm-hmm. So it goes from 1 to less than 10.
Okay. Thank you.
Thank you. That was a good question. Okay, so going back in time, you can see that the structures, in a very simplistic manner, we see a structure and so on. Going back in time, all this structure was all together. So you can imagine that when they were all overlapped, these structures didn't exist as such. It's not as simple as that, but you can see that structures had an origin in the past. And then, as the photons and all the other particles in this primordial soup become hotter and hotter, when the temperature gets to be of the same order as the binding energy of different type of bound objects, these objects are destroyed. So when the temperature of the universe becomes of the order of electron volts, which is the binding energy of atoms, then, before then, atoms didn't exist as such. And you had, so this when atoms become stable, this is the cosmic macro and background radiation emission, as I will explain a little better. Before, there was a plasma in which nuclei, electrons, and photons were free, right? And in this plasma, the building blocks had naked charge, electric charge, so the mean free path of photons was very short. In any case, moving even before, you get to the MeV, which is the characteristic energy, characteristic binding energy of nuclei. And so before then, nuclei didn't exist. This line here indicates BBN, Big Bang nucleosynthesis. And you could go even before, and then there was a moment at 200 MeV, which is the scale of QCD. Before then protons and neutrons didn't exist. So before then, you would have a quark-gluon plasma, and so on and so forth, getting to the point here of inflation. Of course, inflation is a period before the Big Bang, a period of exponential expansion invoked to explain properties of the universe not explained in the Big Bang model itself. One of them is homogeneity and isotropy. We see, for example, the macrowave background radiation coming from far away, large separated, so the regions of the universe that were never in causal contact within the Big Bang itself, never in causal contact, it still look the same. And the causal contact can only happen within the horizon, which essentially is CT. Nothing can travel more faster than the velocity of light. So at any given point, CT is the largest distance in which microphysics can act. And the other is the origin of density in homogeneities, which we really need to explain. They start as quantum fluctuations, and then they are expanded out into astronomical, cosmological distances. We need density in homogeneities to explain the anisotropies of the CMB that I will mention in a moment, and also structure formation. Without them, there wouldn't be any structure in the universe. And I will mention this a little bit better. So after inflation finishes, there is a period of reheating, in which actually, from which emerges the universe radiation dominated, and with a particular temperature that we call the reheating temperature, the highest temperature of the radiation dominated period. And it is not possible exactly to determine what the reheating is. So in spite of the picture that I show you, putting this reheating at very high temperatures, 10 to the 16 GeV or so on, we actually do not know if that is what happened, because the limit is much lower. It's just 5 MeV. And this is because the earliest data from which that we have of the universe, of the early universe, is just the different light nuclei that were produced in BBN. So this is the first proving episode of the Big Bang model. So in this picture, we do not know what cosmology was before this line, which is Big Bang nucleosynthesis. This is unknown. And many of the particles, dark matter particles, it could be stellar neutrinos, etc., are produced then. And so assumptions must be made in order to compute their relic abundance and their relic momentum distribution, etc. So the properties could be different, and I will mention how different they could be actually with making different assumptions about this unknown epoch of the universe. Big Bang nucleosynthesis, it produces only the lighter elements, because afterwards, the universe is cooling all the time, so there is not enough energy to overcome the Coulomb barrier and produce heavier elements. So they produce helium-4, helium-3, deuterium, and lithium-7. The amount of helium-4 is of order 1. The amount of deuterium and helium-3, 10 to the minus 4, 10 to the minus 5. The amount of lithium is about 10 to the minus 10. Very different abundances that we can explain approximately with what we know of cosmology and what we know of nuclear physics. And therefore, we trust that actually we can follow this model of the Big Bang up to that point. And you need the reheating to happen, to have happened a bit before Big Bang nucleosynthesis. Big Bang nucleosynthesis starts in earnest after the temperature is 1 MeV. You need it to be 5 because you need neutrinos to be in equilibrium. Otherwise, neutrinos wouldn't be in equilibrium. Neutrinos enter through the beta equilibrium in Big Bang nucleosynthesis. And therefore, you know that the reheating temperature has to be at least 5 MeV. 5 MeV is very, very different than 10 to 16 GeV. So we don't know, actually, where this is. So the universe is radiation dominated at this point, but later on it becomes, oh, I have to point differently, it becomes matter dominated. We know now that there is much more matter. Matter is about 25%. We know the radiation is dominated by the CMB, by the cosmic background radiation. It's about 10 to the minus 5 of the total density now. But the radiation goes as d to the 4th. Matter, instead, the density of matter is the number density multiplied by the mass. These are not temperature dependent, divided by the volume. The volume goes as 1 over the scale factor cube, which goes as t cube. So while going back in time, this radiation goes as t to the 4th. Matter goes as t cube. So at some point they become equal. This is called matter radiation equality. And this happens when the temperature is about 1 electron volt. This happens very, very near the moment at which atoms become stable. And we don't know why. This is actually a coincidence. We measure the amount of radiation and then the amount of matter now, and we go back in time, and we get when we compute when they were equal. So this is part of our measurements. So a little bit after, you see when the temperature is about 0.3 electron volts, you have this transition in which atoms become stable. So before, you have this plasma in which the mean free path among electrons mostly, Compton scattering, Thornton scattering, non-relativistic electrons, the mean free path is very short. When atoms become stable, atoms are neutral, and therefore the photons that were there present, the mean free path becomes infinite, and these photons reach our eyes right now. Except for the fact that the wavelength, as all lengths, are affected by the scale factor. When the scale factor, as the scale factor increases, moving forward in time, the wavelength of the photons increases too. Namely, it moves to the red. When one says it red shifts. This red shifts makes the temperature of the radiation, this is the cosmic microwave background radiation. Why is microwave? Is microwave now is 2.7 degrees Kelvin, 2.35, 10 to the minus 4 electron volt, which is smack in the microwave part of the spectrum, the electromagnetic spectrum. But before it was much hotter, right? But this is the red shift in the middle. So these photons just red shift. Yes? I cannot hear. Recombination is a misnomer. So recombination comes from chemistry. You know, in chemistry, you put a bunch of atoms, you heat them up, they ionize. You cool them down, they recombine. You know, they ionize, they recombine. This should be combination because it happened for the first time. Again, another misnomer. And of course, we have lost our right of renaming this issue. So this is just a misnomer. Thank you for another misnomer here. Now, we see any epoch in the universe as a surface. Because, of course, from this epoch to now, light traveled, CT, C delta T, from between that moment and us. And so we see it as a surface. This epoch of recombination is also called the surface of last scattering. Last scattering of what? Last scattering of the CMB photons, which interacted with matter last, and afterwards didn't interact anymore. So here we see, we see galaxies within the distance light took to come since the first moment bright galaxies formed. Then, before then, there was this cosmic dark ages that people are examining right now with JW, ST, and so on. They are starting to see the first structures that are formed after the dark ages, how the first structures happen. Without galaxies and a structure, there are no stars. And so there is no light in the dark ages. And then we see the surface of last scattering that corresponds to this moment of recombination in which atoms became stable and the photons that were there are released. So here is represented with this anisotropies in temperature that I'm going to explain now. So you see, 1965 was when Penzias and Wilson, who were building an antenna. You can imagine why they were building an antenna at that point? Do you think that they were looking for the macro radiation? No, they were looking for satellites, Russian spies. This was the Cold War, all right? And the issue is that they saw, wherever they went, they saw this background. Actually, they cleaned the antenna from poop of birds and so on and so forth. They said, we cannot clean the antenna. So actually, there is this thing. And they asked, they were nearby Princeton, and so they asked there, and they said, oh, you discovered that actually the Big Bang is correct. You discovered this light from the Big Bang, this hot beginning of the universe. And so it took 30 years, you see, from 1960s to 1990s, to see inhomogeneities, namely anisotropies, difference in temperature. The difference in temperature are of a few parts in 10 to the 5. So let us say 10 to the minus 4 of the average temperature. And then these anisotropies were measured. You can see the galaxy. The galaxy also emits. And there is a dipole. And so subtracting the galaxy, subtracting the dipole that is due to our motion with respect to the CMB, you can see this. And the color coding is encodes colder and warmer temperatures, but colder and warmer by a part in 10,000, a part in 10,000 with respect to the average. Very small differences. So now this density inhomogeneities that I mentioned, we believe were created during inflation, are absolutely essential to explain the CMB anisotropies and also structure formation, and structure formation with this Baryon acoustic oscillations that are related to the same type of physics that produces the CMB. You see, from a complete homogeneous medium, gravity doesn't do anything in a completely homogeneous medium. You need inhomogeneities, because then gravity tends to make overdense regions denser and voider regions voider, right? And then you produce through this complicated, you produce a complicated structure starting from very small inhomogeneities. Delta rho over rho. Delta rho is the density minus the average density over the average density. This is delta rho over rho. Increases due to gravitational collapse. This is the work of gravity. But you have to start with seeds with inhomogeneities. And these inhomogeneities are producing also the anisotropies in temperature as I will explain. We owe our existence to the same inhomogeneities that produce the anisotropies in the microwave background radiation. And these inhomogeneities are mostly in dark matter, as I mentioned. So this is the way in which these cooler and hotter and cooler regions in the universe appear. So as CT grows, CT is the horizon, it's called, microphysics can act on larger and larger scales. When an inhomogeneity enters into the horizon, smaller inhomogeneities enter it. Yes?
So, sorry, just to double check. So the dark matter is what caused the heterogeneities, or like the seeds for gravity to form?
The admixture of dark matter is more or less the same as we measure now, right? Of all the matter, this has inhomogeneity in everything. These are inhomogeneities in whatever it is, but the matter is mostly dark matter, and then there is a little bit, 15% of it, that is visible matter, right? So that's why dark matter is essential. The characteristic of dark matter are essential for structure formation. So, but at this point, the matter is all mixed up, right? In the primordial mixing. So as inhomogeneities enter into the horizon, there is a little bit overdense. This gravity tends to make it collapse. The problem is that at this point, there is pressure due to photons. Okay, this collapse leads to again an adiabatic compression. Adiabatic compression heats up the medium, right? Heats up. So photons are more active when they are hotter. They produce more pressure. At some point, the pressure of the photons wins over, and this starts expanding. It overshoots the equilibrium position, and when it overshoots, it gets to maximum expansion. There, the maximum expansion, gravity wins over. And again and again. So these are standing pressure waves. They're called many times sound waves, simply because the sound is a pressure wave. It's, again, another misnomer, if you want, but everybody calls about sound waves. There's no sound, of course. Sound is only in air or whatever fluid. But so these are pressure waves. Smaller inhomogeneities have time to go many times. Bigger inhomogeneities that enter into the horizon very close to the moment in which atoms become stable have only time to collapse. In any case, when atoms become stable, photons from all these maximally compressed regions, and therefore hotter, or maximally expanded, and therefore cooler, emit their photons. And you see like a picture, click, of the universe with all the different inhomogeneities. Now, not only that happens, so this is what says photons escape, reach us as the CMB radiation, and show us the hotter and cooler regions as the CMB anisotropies. But also baryons, okay? The baryons are also left without any pressure. Baryons, what are the baryons? Baryons are nuclei, right? We call baryons protons, neutrons, nuclei. So baryons are left. So there were inhomogeneities that were expanding, and at some point, boop, the pressure disappears, and they are left there. Now, in the middle, they are left there, and this produces what is called baryon acoustic oscillations, BAO, in the matter power spectrum that I will mention. So here it is that in a region with high initial density, where there was high pressure in the baryon photon fluid, which propagated as an expanding spherical sound wave, sound pressure wave. Now, after recombination, the photons go off with the speed of light, and baryons are left sitting in a spherical shell around the initial excess density, mostly of dark matter. Dark matter is not affected by all this. Dark matter all the time, pop, 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 continues being gravitationally, yes, but bound, right? Continues growing delta rho over rho in matter. Yes, I can repeat if I can hear you. What? You will see what it is in a moment. Period is not really a period per se, because it is, I will show you what they call the baryon oscillations. They are wiggles in the power spectrum. So again, they are called oscillations, but in the power spectrum, actually. So these are, so there is a shell, characteristic shell, characteristic shell, characteristic distance, but there is a potential well generated mostly by dark matter. Part of these baryons that are in the shell fall back, but part of it stays there, and it evolves in the universe. And so then you can see that there are preferential distances right now in which you will find, more likely than not, a galaxy with respect to another one. Now, how is this shown, actually? Okay. So we make a description, both of the CMB and isotropies and the matter spectrum, by using this description. The amplitude of the fluctuations as function of a scale is quantified by what is called the power spectrum, P. It will be P of k in a Fourier expansion, which is essentially the square of the Fourier amplitude as function of k. Now, as I said, for the CMB, we don't have 3 dimensions. We have only 2 dimensions. We see that an epoch as a sphere. And therefore, you have, on a sphere, you have only 2 angles, right, as variables on a sphere. And therefore, it's not really a Fourier transform with k a vector, but we use spherical harmonics, and this number L, the principal number L, is related to the different type of spots that you can have, the angular dimension of these spots. And this is the angular power spectrum. You can see is about the square of this expansion in spherical harmonics. And this has been measured exquisitely, by Planck in 1913, 1915. The Planck satellite. Before, we had only the first 3 with large uncertainties, and then after Planck, you can have this marvelous depiction of these 7 peaks. By the way, this shows the square of delta t over t, if you want. So the first peak corresponds to the maximum compression. The second peak is maximum rarefaction. The third peak, maximum compression, and so on and so forth. Yes?
Pode perguntar em português, traduz.
Okay. Well, sí. Antes. Después. L and M are the numbers that you have in all spherical harmonics. L and M corresponds to how many, I don't remember now. I'm not sure I can. So this is a picture of the universe. You have seen, this is what is called a Molveide picture of the universe, equal area. You have seen pictures of the world, right, of Earth in that shape. So this is the galaxy is here. This is the plane of the galaxy, and so on. So you have to picture this. And so L and M indicate how many structures you encounter moving in one direction and in the other. So essentially, there are features. The spots correspond to about 2 pi over L, the size of the spots. Is that what you were asking? Okay, so they correspond. So you see, larger L correspond to much smaller spots. And then, of course, you sum all these spots with different amplitudes, and then you get the map that you have. Okay. Yeah. So, by the way, in all this data here, you see a blue line. This blue line is not a fit to the data. It's actually the line that corresponds to the model that we have, lambda CDM, where lambda stands for a cosmological constant, namely a dark energy that is a constant density in time, and the CDM is called dark matter. So this is not a fit, it's actually a prediction of the model. Now, there is an enormous richness. I'm not going even to cover. This would be a course in cosmology, actually. Yes, go ahead. But for example, there is an enormous amount of information here, but the position of the first peak tells you that the universe is spatially flat. Yes?
You used the spherical harmonic, right? And this assumes that we need to have this symmetry and azimuthal symmetry, right? Why this is a good approximation for the universe?
What this requires is to have random processes. So this explains the distribution as a random process. Namely, we don't know exactly why one spot is there and the other spot is here. But we can explain in this way the distribution of spots. Is that what you want?
But, so you're not using the azimuthal symmetry, for example?
Azimuthal symmetry?
Yeah, to use
I don't think that this uses azimuthal symmetry in particular. It uses just the Fourier transform. It's like a Fourier transform. In Fourier transform, you can produce through a Fourier expansion any function that you want. And this is the same, except that it's in the 2 dimensions. It's nothing more than that.
Okay.
Yeah. So I don't think that there is an explanation, any other assumption.
Thank you.
So the universe is spatially flat. Namely, if you pick up any triangle, the sum of the at larger scales, the sum is 2 pi. Sum of the internal angles. Is 2 pi. Yes.
Sorry, the universe was flat or is flat right now?
Is flat.
Right now.
And was flat.
Okay, great.
Was flat, is flat. Yes, it's very close to flat. In fact, if it was not flat, it approached being flat. No, it deviated from being flat. So in the early universe, it should have been even flatter. Namely, how we quantify that? Because we have a critical density, which is the value that you need in order to be precisely spatially. There is curvature, right, in 4 dimensions, in the 4th. But in a space, there is no curvature. And actually, we measure one. We measure actually that the difference for one is 0.00. And like in the 4th or 4th place, there is some difference. But the difference we measure now, Planck measures it and so on. And so going back in the past, you can see how it would change, and it will be even closer to 1 if it is now 1. Yeah.
Okay, but how can say the difference between kind of local flatness or global flatness?
What does it mean, local flat? No, this is all local
universe.
flatness. This is local. This is local flat. What do you mean local flat? We live in, you mean the topology?
Yeah, kind of.
Well, no, but the topology is different. No, I'm talking, so you know, if you have a piece of paper, you could have it flat. What he's referring to is that maybe this piece of paper is like this, right? Forms a cylinder, and then I put this to, I cannot do with a piece of paper. You have to do with your imagination. If I identify these 2 things, I will have a donut. A donut is indistinguishable, of course. It's still flat. So this is always local curvature, right? Definition. Yeah.
My question is, can be silly, so sorry for that, but I was wondering, we can get information from the CMB anisotropies of the geometry of the universe, dark matter, and etc. But what about C nu V, if detected? We can learn something about the...
What about what?
C nu V.
C?
Nu V.
C, nu.
V.
The
Is
cosmic
the
neutrino background. The day we will measure it, yes,
Yeah,
we
but
can measure. We could learn a lot, but it is extremely difficult to measure. Actually, yes. So yes, the cosmic neutrino background would be fantastic to measure, but it's so difficult.
Yeah.
So yes, of course. Now we just compute it, assuming this, assuming the other. There will be some indications probably, because as I will say, neutrinos are were hot dark matter, but at the moment they become non-relativistic, they help in structure formation. And so it could be that in the next measurements, or even in the next generation of CMB measurements, we will have some handle on the mass, maybe the number, who knows. Yeah, but of course it would be fantastic, but we don't measure. We can see with exquisite precision photons, but neutrinos in the background. Yeah. Any other question? Okay. I'm very glad. So we are in a very good start, right? With question. Okay. Yeah. So now the matter spectrum. Of course, the matter does the same thing, but with the distribution of galaxies and so on. They are in 3 dimensions. So we have an honest Fourier transform with an honest vector and an honest K vector. And it is the same. The power spectrum tells you essentially the distribution. You see this is the square. This is the power spectrum. It's essentially the square, as I mentioned before. I don't want to enter into all the details. So this is the power spectrum. And you see these little wiggles. So this is the Baryon acoustic oscillation. What oscillates is here, the power spectrum, here. This was measured starting in 2000, 2005, so, but 2012, 13 was much better measured, okay? So here you have different spectra, different K, and so on. These are these autocorrelations. So it is in this at this radius, you have, if you have a galaxy, the probability, the likelihood of finding another galaxy at a particular distance is larger at particular distances that are given by what happened at the moment of the last scattering. Yes? This. You see this little... Yeah, the right side is what remains if you take out the average here. You can see these little wiggles. Assume that I subtract the blue line. Is blue? Black. Okay? You subtract it, and then you get that. So you subtract this average, and you can see it even with your eyes, really. You can see that, but of course here you see them much better. And these are different, you know, I'm not a cosmologist. I'm come to astroparticle physics from elementary particle physics. So don't ask me exactly what that means, all these things. These are different tracers, different type of objects that they used, and they have different wiggles. Okay, yes. All right. So, and you see that actually the role of dark matter is essential in explaining CMB anisotropy spectrum and the large scale structure and the Baryon acoustic oscillation. Yes?
Is it a fit or a prediction?
No, I think this is a fit. I don't know. I didn't check. But of course, you have to explain this. I think this is a fit. It's not a prediction. Huh? It says that it is a fit? Okay. Features, best fit. It is a fit. And thank you. It says so. But the role of dark matter is essential in explaining the CMB anisotropy spectrum, the larger scale structure, and the baryon spectrum, baryon acoustic oscillation spectrum. So it's not only galaxies, galaxy clusters, but it's all this early, very precise early universe stuff. Now, so here we start with the properties. What we know after 90 years, as I said, the problem had been with us since the 1930s. I will say that at the end, we will have here a page of properties. So after 90 years, we are going to be able to have all the properties that we know of dark matter in one page, after we understand what every single line means. The first thing is that it has attractive gravitational interactions, and it must be stable, or it has a lifetime which is much larger than the lifetime of the universe. We can consider actually dark matter that is decaying, but of course the bulk of the decay will happen in the future. This is still around. So far, we haven't been able to find a good modified dynamics plus only visible matter model that replaces dark matter. That doesn't mean that it doesn't exist. It means that so far it hasn't been found, and I will have a comment about this. The issue is the following. We have no evidence for dark matter in any other way but gravitational interaction. So we trace dark matter in the same way Uranus and Neptune and so on were found, through the effects that these things that we cannot see have in objects that we can see. That's how we do things. And so there is always this question that will be there. Could departures from the law of gravity itself explain the data instead of dark matter? So could we modify gravity and have only the dark matter, only the matter that we know we have in atomic matter, and still explain everything? Of course, this idea is an idea. It will always be there, but we cannot test general ideas. We test particular models. And so it is very difficult for any model to explain all the effects that the dark matter effect explains. Not only galaxies, clusters of galaxies, larger scale structure, but also the early universe that I have mentioned before. So, so from time to time, there are models that appear to replace dark matter. A very early one was MOND, Modifying Newtonian Dynamics. This was 1983. Very soon, as it was understood, it tried to explain just why the orbital speed of is flat, constant orbital speed in galaxies. But of course, you need covariant generalizations to go to things in the early universe. And one of them was this tensor vector scalar, TeVeS, that was in 2004. It failed to explain the CMB and BAO precision data in 2015. So it took 10 years to actually kill this model entirely, and I will mention how it was killed. There is another claim by Skorkis and Slotnick in 2021. And this is for another extension of MOND, which is called Ether Scalar Tensor, EST extension of general relativity. And the authors say that it agrees with all the phenomenological tests which have so far been made. Now, there are predictions already that are slightly different from the predictions of dark matter. And we need, this means that I have 3 minutes, because otherwise I forget. Okay? So let us finish this thought in 3 minutes. What is MOND? For those of you who have never seen MOND, MOND is a very simple idea. It is that force times mass, force equal mass times acceleration is changed, actually. For very small accelerations as those of these structures, luminous structures in the periphery of galaxies. And instead of having A, you have A squared. So you see that since you have A square and A is a centripetal acceleration, which is V square over R, on the right-hand side, now you have B fourth over R square. And since the force also has an R square, and R square go away, and you have a velocity that is constant. Now, this was supposed to be, A0 was supposed to be universal constant, blah, blah, blah. It is not actually. Even to explain the morphology of galaxies, you have to change A0 and that. So, you know, better data means more problems for this. But also, there was a problem with this structure. This is called the bullet cluster. This is called the bullet cluster because of this shape here, which is a wavefront like you would see in a bullet in slow motion, a bullet passing through a medium fluid has this shock wave in it, and so it's called the bullet cluster. So this is an image that superposes measurements of X-rays of hot gas and measurements of where most of the matter is, that is there in blue, that is obtained by gravitational lensing. So this this piece of a cluster consisted of two parts that pass through. When passing through, the interacting components, which is the gas, stayed behind. It interacted, scattered, and so on. It stayed behind. And most of the matter passed through. This segregation from where most of the visible matter is and most of the matter is, the segregation is very difficult to explain, actually. And even Tevez needed to claim some dark matter. So already couldn't explain this alone. But then also, here you have, I stole these slides from a very nice discussion that actually Dan Hooper had with a debate, Erik Verlinde, which you can hear is very entertaining. In any case, before the 2015 measurement of the spectrum, the spectrum of Tevez was okay, was marginally okay. It could explain sort of the first three peaks, but then with the 7 peaks, it failed. It failed entirely. And not only then it failed here, but also, again, you can see these little wiggles that I introduced you. These are the Baryon acoustic oscillations. And then the Baryon acoustic oscillations would be very different. In a universe without dark matter, these oscillations should be much larger. Why? The amount of matter that would remain would be much larger. As I said, part of the baryons in these spherical shells falls back, attracted by the dark matter in the middle. Without that, the oscillations, these variations in the power spectrum will be 30 times larger than observed above. So, so far, this new model that was proposed 3 years ago say that they actually can account for all of this. We'll wait a little bit more. And you know, these are very complicated models. Not many people are working on them. And so we'll see. And in about 10 years, I will tell you if it fails or not. My hunch is that it will fail. But you know, people are very creative. And let me see. Okay, I think it is a good a good moment to finish here, and then we are going to continue tomorrow with the third property.
Thank you. So now we go for a coffee break. We come